So now I want to present sensitivity analysis to methane and what reactions are important in to ignition delay time, flame speed, and to methane ignition. And how do we then determine or arrive at a rate constant that we want to use in the mechanism? Okay, and it give you some idea of the way we do it. Okay, so if we look at flame speed, it's nothing new. We have H plus O2 gives O plus OH. We have HCO plus M giving H plus CO plus M. We have CO plus OH giving CO2 plus H. Okay, these are the three most important reactions increasing the reactivity or increasing the flame speed. Okay, so where do I get the H plus O2 gives O plus OH rate constant from? Where do I get the HCO plus M giving HCO plus M reaction from, rate constant from? And where do I get the CO plus OH giving CO2 plus H rate constant from? And then I go down through the list, maybe not all of them, but I give you a sense and a flavor of the rigor that we go through in assessing the rate constant and arriving at a rate constant for each reaction. Okay? So the first one is H plus O2 gives O plus OH, and this is taken from the Hong Fit, and this is from the study that I showed you earlier today from Professor Hansen's group from his shock tube, where he measured the water profile. He looked at the sensitivity to that, and it was in the H plus O2 gives O plus OH rate constant, and then he reported the rate constant. And that's the rate constant that we use in the mechanism. And then this is a more up-to-date slide of the various data that's available in the literature. Okay, and you can see that rate constant fits the data quite well. And again, one thing I should have said, and I would have said it, you see such high sensitivity that even a 5 or 10% uncertainty in that rate constant would have a big effect on model predictions. So because it's so sensitive, if you change it by 5%, it'll have a big effect on your model predictions. Okay, so it really needs to be known to a high degree of accuracy, particularly that one. Okay, but this is the rate constant we use, and that's what's in the mechanism. Okay, then if we look at CO plus OH given CO2 plus H, we actually use, this is a fit from Hai Wang and Joshi, published in 2006, and you can see here actually there's a low temperature end and a high temperature end. So the rate constant varies from here up through here. And then this is just a close-up of the curve part here where there's quite a bit of data. Okay? But so we use a duplicate rate constant in this case. So we have one expression at 7.015 10 to the 14, t to the 2.053, with an exponent of a negative activation energy of 355.7 all over RT. And that's for this part here, okay, at high temperature, okay? And you see there's a strong temperature dependence of t to the 2, okay? And then in the lower temperature end, we have this expression here, which matches this curve here, 5.757 times 10 to the 12, t to the minus 0.664, and then an activation energy of 331.8 calories per mole. Okay, and then if you calculate the rate constant as the sum of those two expressions, you get this solid line prediction of the data. Okay, and that's what's in the model. Okay, and we haven't messed with that over the years. Okay. So another one, O plus HO2 giving H2O plus OH. Okay, again, here's the data that's in the literature. Here's a rate constant recommended by Burke et al. Here's another one, again, from a study from Ron Hansen's group of the same one. They're similar, okay, but you can see that this rate constant comes through the data. Mike Burke's rate constant is a little bit low at 2000 Kelvin, okay? But So we're using the red curve rate constant in our mechanism. Okay, I'm going through this, and I will be boring, but what the theme, or I want to highlight from the get-go, the theme is, look, we plot the rate constants where we can as a function of temperature, and then we take whatever is in the literature and we scrutinize that, and then we choose what we think is the best rate constant for that reaction. Okay, that's what we're doing. Okay, here's one working with Stephen Klippenstein. Okay, so this Klippenstein et al., I'm one of the et als, okay, on this, but it was actually Stephen that did all the work on calculating HO2 plus HO2. It was in all mechanisms up to 2019, there was a duplicate fit to that, producing H2O2 plus O2. Okay, so there were two reactions again, because you have this fit here, and then you have this piece here at high temperature. Sorry, at low temperature you have this reactivity. At high temperature you have this reactivity, and to get that curve, you had to have two expressions, two Arrhenius expressions, and it was a fit to both. Okay, but actually, what Stephen found was, he calculated this dashed expression for the channel giving you H2O2 plus O2, and this dot dashed branch giving two OH radicals plus O2. So what's happening here is that actually you've got, and this happens sometimes, right? You have HO2 plus HO2, right? It gives H2O2 plus OH, right? And then, plus O2, we should say. And then H2O2 can then decompose to give OH subsequently in its plus M reaction to give OH plus OH plus M. Okay? Right, so that would happen. But actually, there's some excess energy in the system, and about 10% or less of the HO2 plus HO2, when it reacts, 90%, so Stephen calculated that 90% goes to H2O2 plus OH. But there's enough excess energy that the H2O2 can break directly, and through being chemically activated, to give directly OH plus OH. Okay? And so that's what this dot dashed curve is here. But that actually makes a big difference to the hydrocarbon mechanism. So even though it doesn't look very significant, right, and it only becomes important at 800 Kelvin, actually, because HO2 kinetics is so important at 800 to 1200 Kelvin, this little bar here makes a big difference to the reactivity of all alkanes, or all fuels, in that temperature range. And having that 10% going directly to two OH radicals plus O2 significantly enhances the reactivity of predicted fuel reactivity for fuels in that temperature range by adding that. Okay, so that was important. Okay, but you can see Stephen's calculation is the solid line, and it matches very well, certainly with an experimental uncertainty, the rate constant measurements that exist in the literature. Okay. Here's another one, H2O2 plus argon giving OH plus OH plus argon. So here again are experimental measurements in the literature. Here's we have a fit to this rate constant. We have the Matsugi 2021 calculation, which we believe better matches the experimental data here, okay? Because the Troe overpredicts the Sajid et al. 10 atmosphere data here. The Matsugi does a better job of capturing that pressure dependence. So now actually in our mechanism we're using the Matsugi calculated rate constant, okay, in our mechanism for this reaction. So you can see at low pressure, the reactivity is lower. The higher in pressure you go, the higher the reactivity. But it's not at its high pressure limit. You see at 10 atmospheres here, it's maybe 2 orders of magnitude lower than its high pressure limit, okay, at 10 atmospheres. You'd think 10 atmospheres is fairly high pressure, but it's not in this case, okay? Another one is H plus O2 plus N2, giving HO2 plus N2, okay? And this is, again, we're taking this calculation and derivation from this work published in 2020, okay? And we're using that now in our mechanism. And you can see it tends to better match or fit, it's a better fit to the experimental data that exist there, okay? And so that's what we're using for that, okay? Here's H plus O2 plus argon giving HO2 plus argon. Again, we're using this red solid line, okay? And it's a better fit to the experimental data, okay? Another one, O plus water giving 2 OH radicals. We're using this red line fit to this rate constant. And that comes from Tan Lam Nguyen and John Stanton from 2013, right? So, but what's the theme? The theme is, look, you go to the reaction that you want, you know, each reaction in turn, particularly for the hydrogen-oxygen system, we plot the rate constant that exists in the literature, and we take the best fit that we can to that data so that we can include that rate constant in the mechanism, okay? There's no hand waving, we're taking the best fits we can, okay? And it's very soundly based, okay? Here's 2 more reactions, okay? So I went on, some of them are in the hydrogen-oxygen mechanism there that are not in the sensitivity, but if we look at the second most important reaction, enhancing reactivity is HCO plus M. And again, one thing I should have said at the start, look at every reaction. Here's to methane flame speed. What should we be looking for? Hydrogen atom, okay? And what do we see? Hydrogen atom, hydrogen atom, hydrogen atom, okay? Hydrogen atom, hydrogen atom, hydrogen atom. Nearly every reaction has hydrogen atom in it. There's very few that don't, okay? And again, because why, I didn't really explain why hydrogen atom is very light. That's the thing, like it's one proton. And so it can diffuse across the flame where not even molecular oxygen diffuses like hydrogen atom, okay? So it diffuses like crazy across the flame, and hence it's so important in flame predictions, right? But 2 reactions here anyway that are really important are the one HCO reacting to give H atom, which enhances reactivity, and then if HCO reacts with O2, it doesn't give H atom, it gives CO plus HO2. And so that inhibits reactivity, right? So the one producing H atom enhances, the one that doesn't, competing with that doesn't, reduces reactivity. Why? Because H atom that's produced here would then react with O2 to give O plus OH, right? And so where do we take the rate constants for HCO plus O2? Again, we plot them, and then we're using this Hsu et al. 1996 rate constant in our mechanism, okay? And then we plot HCO plus M, giving H plus CO plus M. And you can see, one thing I want to plot out, or point out here. Here's, I don't know what the dot dashed is, maybe I'll come back to it. But this one is a rate constant that was in a mechanism, I pointed it out earlier, Lee and Dreyer, a mechanism that was published here from Princeton in 2007. And then we increased that rate constant by 20%, which is that solid line. And you would say, look, what's 20%? And you can see in the plot here, it doesn't look like much, right? And they're both acceptable fits, which they are, okay? So sometimes we have to adjust the rate constant within the uncertainty, okay, limit, okay? And why am I talking about this? Because let's look. Here's HCO plus M, right? We saw that it was the second most important reaction in flame speed simulation for methane, right? But actually, it's the most important, sorry, it's the second most important one too, but it's nearly as important as the H plus O2 for methanol. And HCO plus O2 giving CO plus HO2 is the most important reaction inhibiting the flame speed in methanol. So the HCO kinetics in methanol is more important than it was in methane. Does that make sense? Why? You agreed, why? Yeah, but why is HCO chemistry more important in methanol than it is in methane? Because look at the structure. You have CH3OH. What's methanol going to give you? It's going to give you hydroxymethylene or methoxy. But what are they going to give you? They're going to give you formaldehyde, which is then going to give you formal radical. So the concentration of formal radicals in the methanol system are going to be even higher, very high, in comparison to their concentration in methane. So it's important in methane, but it's even more important in methanol because those pieces are coming from the fuel almost directly. Okay? So you see here that they're even more important here, right? So we need to look at them. Okay, so this is a little story, and the story is not to say, look, our mechanism is better and the other mechanism is worse, right? The story is to say what we do and the kind of analysis we perform to try and improve the mechanism and trying to reason out, well, what's the right story, right? And what's the right thing to do as best we know, okay? And it's just an example. So take it on board. So here, the solid line is the Aramco-Mech prediction, okay? And if we take the Lee et al. Rate constant for HCO plus M in Aramco-Mech, we put it into Aramco-Mech, the simulation goes from the solid black line, which wasn't perfect at the start, but it was better. It goes from there to the dashed line, right? So, and what was the difference? The difference is just we were 20% faster in the rate constant for the HCO decomposition in Aramco-Mech compared to the Lee mechanism, okay? But that 20% has this predicted change in the flame speed. And it's certainly more than 20%, but it's a big change, right? And it's a big underprediction of the flame speed, right? So if you then take the Lee et al. Rate constants and we include the HCO plus M giving H plus CO plus M as we did here, okay? And we take the CH3OH plus OH giving the methoxy plus H2O rate constant, it actually almost matches perfectly with the Aramco-Mech mechanism, right? So the point that I'm making here is that there's some compensation in the rate constant that is used in the Lee et al. Mechanism in this rate constant that's compensating for the slower rate of HCO plus M, which then brings it back in line with the Aramco-Mech prediction. So the question then is, should we have changed that rate constant by 20%? Or is our rate constant wrong for that reaction? So who's right and who's wrong for that one? And again, that isn't the point. The point is, what is the correct rate constant for that reaction is the question, right? And so let's look at it, okay? So methanol plus OH gives methoxy plus water or gives hydroxymethylene plus water, okay? If we take the total rate constant, and here's the total rate constant plotted in the literature versus, this is the rate constant versus inverse temperature. You can see that there they are, and here's a fit by Bott and Cohen, right? And it captures the data quite well. And here's another fit. Again, Bott and Cohen, I think, was published, I don't know when it was, but it was the 90s or something like that. And then this Zhu and Lin was published in the noughties sometime, right? So quite a long time later, okay? And you can see actually it's a better fit to the data, okay? But you would say both of them are acceptable actually, right? They're not bad, right? But if we look at the Ray constant from Zhu and Lin and Bott and Cohen, you can see that there's quite a difference in the branching ratio. Zhu and Lin say there's very little methoxy plus OH, and you get 95% or more hydroxymethylene plus water from that reaction, okay? But Bott and Cohen say that if you go certainly up to close to 2000 Kelvin, that the branching ratio should be about 50-50, okay? Zhu and Lin said no, right? It only goes to not even below 90%. It's still over 90% hydroxymethylene plus water, okay? So then, there still isn't a lot of evidence, right? And this is where we have to kind of do some exploring and reasoning, right? So, apologies. So here's the Ray constant. So if we take any alcohol plus OH, producing an alkoxy radical plus water. In other words, abstracting the alcoholic hydrogen atom, right? They should all be similar because you're abstracting a hydrogen atom which is bonded to an oxygen which is bonded to an alkyl group, right? And it shouldn't depend very much on what the alkyl group is. It should depend more on the bonding to the oxygen atom, okay? And here are some calculations performed, or Ray constants from the literature for methanol, ethanol from Sivaramakrishnahan, and then Chongwen Zhao calculated it for M-butanol. And you can see that all of these Ray constants are down here. Now, that looks like a big spread, but actually there isn't a wide range here. So it's certainly these are within a factor of 2 of one another, right? But here, the Bott and Cohen Ray constant is up here. And it looks like this is 2, 3, 4, 5. It's a factor of 4 or more, maybe a factor of 5 too fast, right? It's certainly much faster than the others. So that Ray constant looks to be too fast, right? So you should use, in our opinion, you should use the slower rate for that reaction. And if you do, you can then use a slower rate for HCO plus M, giving you slightly faster rate, I should say. Anyway, the compensation. But it seems like one was compensating for the other, but the Ray constant that we had in the mechanism was more reasonable. Or we made it more reasonable by doing this study, is really what I'm trying to say. Okay, so the next most important reaction, inhibiting flame speed, is methyl plus H giving methane. And actually, it's kind of ironic, and it isn't happening the way you think it is. So because methane is the fuel, you would expect that this reaction is happening in the reverse direction. Methane gives methyl plus H. But it isn't. It is actually happening in the methyl plus H giving methane direction, right? So it's actually consuming 2 radicals, producing methane, right? And not happening in the reverse direction, right? Ironically, right? And so if we increase the Ray constant of this reaction, what that will do is not increase the reactivity, but actually decrease it, because it's consume H atoms and methyl radicals, producing a stable molecule, okay? But particularly H atoms, because that's the important one in the flame, right? And where do we take the Ray constant from that? We take it from the calculations by Stephen Klippenstein. He has a high pressure limit, and then these are Ray constants that he calculates as a function of temperature. These dotted lines are the Ray constants that exist in GRI-MEC. So actually, his calculations match, well, our GRI-MEC match his calculations, or the two of them are in agreement at very low pressures. But as you go higher in pressure, his calculations are lower or slower than what GRI-MEC use. Okay, why am I talking about that? Because if we look here are flame speeds for methane measured at 1, 5, and 10 atmospheres. And then these are model predictions. So again, the solid curves are Aramco-MEC model predictions, and then the dotted lines are GRI-MEC predictions. Okay, the data are taken from Lowry et al., which is from Professor Eric Peterson's group in Texas A&M University. Okay, and what we see is that one thing I want to point out: the solid line is Aramco-MEC prediction. Then the dashed line, is GRI-MEC prediction. But if we take all colliders, all third-body colliders in the methyl plus H plus M reaction giving methane plus M, and we reduce them to 1, right? The GRI-MEC prediction changes from the dashed line to the dotted line, right? It means that actually it overpredicts the flame speed at 1 atmosphere, but it actually matches almost perfectly the flame speed at 5 and 10 atmosphere, right? Now, these third-body efficiencies are kind of hand-waving, and I know Aaron Jasper, now working at Argonne Labs with Stephen Klippenstein and that group, he's doing some more calculations on these third-body efficiencies, and we know more about them, okay? But we need that kind of work because the third-body efficiency does make a difference. And so what we're seeing here is, look, the prediction, particularly at high pressure, was too slow. It becomes faster at higher pressure. Why? Because if we reduce the efficiency, what are we doing to the rate for methyl plus H plus M? The M concentration decreases, the rate of that reaction decreases, and hence we don't get as much termination of the recombination of methyl with H giving methane as we were before, and hence the reactivity, the predicted flame speed is enhanced, right? So sometimes you might ignore the third body efficiencies and then think, oh, they're not important. In this case, they're very important, right? And we as a community need to pay more attention to those, right? Okay, so let me skip through here. Here's something that actually Yuki Murakami, working in my group, he looked at this. So Aaron Jasper did calculate the, this is the Leonard-Jones parameters, those transport parameters for H atom, okay? So, and these are important. So here he's plotting a relative energy versus molecular distance. And so at what we have, does everybody understand the Leonard-Jones 12-6 potential? Have you studied that? Did you hear that? Okay. So there's a potential energy calculation between two atoms. In this case, we have HO2 and the collider, right? Or anything and the collider, right? And it depends on the energy and then the inverse 12th power on repulsion and the inverse 6th power on repulsion. What am I thinking? Yeah. And it's called the Leonard-Jones 12-6 potential because of this. Okay. So this is an attractive force here. This is a repulsive force here. And so what we see is that as we become closer, as the two moieties become closer, there's an inverse 6th power attractive force because this is negative, and then this is positive. This is a repulsive force. Okay, and it's to the power of the R is to the power of 12 for repulsion, and it's to the power of 6 for attraction. So as the species become closer and closer together, you can see that the potential energy of interaction between species goes very, very positive very quickly, the closer you get, because it depends on the 12th power rather than the 6th power. Anyway, if you take this into account, you get these curves for the potential energy of interaction between the collider, which is H atom, and other species. This dashed line represents that potential energy of interaction, taking the parameters that we had in our mechanism and the parameters that were taken in most mechanisms up to the calculation by Aaron Jasper in 2014. Okay, this was published in 2014. But actually we hadn't taken it on board, and most mechanisms haven't. Okay, so we put it into the mechanism, okay, and I'll show that in the next slide, but it didn't work, right? So we actually adjusted. So here, this solid black line represents the potential energy of interaction of, and the minimum energy of a H atom reacting with another moiety, okay, with the transport parameters, the sigma. Sigma here is the interatomic distance at zero potential energy of interaction. Okay, so sigma that was calculated by Aaron Jasper, where is it? Was at 1.5, is it 1.53? Okay, so the calculated sigma is 1.53. Okay, the energy barrier is 541.67, or the energy well depth, I should say, is 541.67. Okay, so what we did was we kept the energy well depth for the interaction at the same energy well depth, but we changed the interatomic distance at which the potential energy of interaction is equal to 0 to be 1.842 angstroms, as compared to 1.53 angstroms. When we did that, we get this prediction. So the dashed line is the prediction using the Lennard-Jones parameters, the transport parameters that we had in the mechanism, right? And you can see here at the 1 atmosphere and 298 Kelvin, the mechanism didn't quite match the data. When we included the Jasper calculated Lennard-Jones parameters for H atom, the transport parameters, we got the solid line predictions, which overestimated the flame speed slightly with our optimized kinetics. And then when we adjusted just the sigma at zero potential, we get the red line predictions, which match the data. So again, that's another parameter that we use, and again, it's a fitting parameter, right? It may be wrong, but it's a 60% difference in the sigma, this interatomic distance that's considered in the Lennard-Jones parameters. Okay, but that's what we had to do to get good agreement with the experiment. Okay, I'm changing from flame speed to ignition delay time, and this is at intermediate temperature and high pressure. And here you see a lot of reactions that involve both OH and HO2. Okay, OH, HO2, HO2, OH. CH3O2 is also important. Okay, but most of these involve HO2 and OH. And you can see methyl plus O2 is very important, and methyl peroxy plus methyl is very important. Okay, that gives you 2 methoxy radicals. So this is very important at low temperatures. So where are we getting those rate constants? Okay, the methyl plus O2 we're taking from different places. The methyl plus O2 giving plus M giving methyl peroxy plus M from Fernandez. Methyl plus O2 given formaldehyde plus OH. This is private communication with Stephen Klippenstein. And then methyl plus O2 giving methoxy plus O from Srinivasan et al. Okay, I think he was working with Joe Michael. Okay, but actually it's not an important pathway. Okay, in my opinion, it's not an important pathway. But here we look at sensitivity though to kinetics, and we see here that there's high sensitivity to the entropy of CH3O2. There's some sensitivity also to the entropy of O2 and methyl, but they're fairly well known. So if we look at methyl plus O2, giving methyl plus O2, the only species that's less well known is methyl CH3O2. So in our mechanism, originally, well, actually, there's high sensitivity to the entropy, but the entropy that we had and the entropy that we calculated, well, it was by John Simi, are about the same. But actually, the heat of formation, and there is some sensitivity to the heat of formation too, you see it there. The calculated value, the more modern calculation, is 0.7 kilocalories per mole higher than what we had before, right? So what does that do? Okay, so we have this, I'm not going to go to, we have this sequence. Methyl plus O2 gives methyl peroxy. If its heat of formation is 0.7 kilocalories per mole higher, it means that it's 0.7 kilocalories per mole more difficult to produce CH3O2. So that drives back this equilibrium back towards reactants, to the methyl plus O2 direction, okay? And then if we get less CH3O2, a lower concentration, we get a lower concentration of methoxy radicals. What will methoxy radicals do? They'll decompose to give formaldehyde plus H, or react with O2 to give formaldehyde plus HO2. But they're going to give you some reactivity, okay? So if we produce a lower concentration of CH3O2, it's going to decrease the reactivity of the system. And the thermochemistry will dictate in this case, because we've increased the activation energy 0.7 kilocalories per mole, that we're going to get less CH3O2. So this is what happens. So the original model prediction is this dashed line, and then just changing the activation energy, the enthalpy of formation of CH3O2 by 0.7 kilocalories per mole, the reactivity decreases by a factor of 2, right? That's just the thermochemistry. So, and again, it's showing the importance of having accurate thermochemistry in the mechanism, right? Here's looking at the CH3 plus O2 giving CH3O plus O channels. Here's a measurement by Ron Hansen's group in Stanford. Here's a measurement by Joe Michael's group in Argonne National Laboratory, both published within 6 months of one another in 2005. And then we actually used the Srinivasan ray constant in our mechanism. But you can see that down here, there's about a factor of 7 difference in the ray constant. But actually, it's not the dominant channel for the reaction of methyl with O2. What is the dominant reaction is formaldehyde plus OH. But here again, here's a measure or a calculation or a measurement, a ray constant from 1995. Sorry. Here's the measurement by Herbon from Stanford group. Here's a measurement by Joe Michael in 2005. Here's one from 2007. It's a bit slower, okay? And then here's one that was calculated by Dr. Stephen Klippenstein at Argonne Labs, okay? So it paralleled the Herbon one, but it was always faster than it, okay? And I actually, so this Stephen calculated because I asked him to, and he sent me the ray constant, right? But when I was optimizing my mechanism and trying to optimize the ray constants in the mechanism or to fit the data, I actually arrived at a ray constant that was within 25% of the red line that he calculated. Okay, so what am I trying to say there is that oftentimes to optimize the mechanism, I will adjust the ray constant to fit the data that we have. And as long as the data is reliable, the data is actually telling you something. And it's telling you where the ray constant should be. And if you have particular sensitivity to that reaction, it will tell you what the ray constant should be. Okay? I hope that that's useful. that's just showing different branching ratios and different branching ratios, and then that's just showing you the choice of rate constant from different mechanisms. The only thing I would say here is that the rate constant in the San Diego mechanism doesn't seem right at all. Okay, other ones are tolerable. Okay, I won't go into that. Okay, so two other ones. So we have methyl plus O2 giving formaldehyde plus OH. We just spoke about that. So this is sensitivity analysis, again, at 30 atmospheres, okay? This one is the most important reaction, increasing reactivity, okay? Another one is this one, CH3O plus oh no, I've already spoken about that. Okay, so where are we getting this rate constant from? You can see here that there were some measurements of this reaction giving 2-methoxy radicals from CEFRC from 1988. And here, the pilling fit is a little bit fast. Actually, at low temperature, it matches well, but at high temperature, it tends to be a little bit fast. So what we've done is we've refit, and we're fitting to the higher temperature one. When I say higher temperature, this is 500 Kelvin here, okay? So you can see that the red line here is more in line with what you'd expect to see at combustion relevant conditions, because it's matching the data at the higher temperature combustion relevant conditions. This is very low temperature. It's down below room temperature, okay? Okay, methane plus HO2 is also very important. And the channel producing methoxy plus OH enhances reactivity. The channel producing methane plus O2 inhibits reactivity, okay? And so the accurate rate constants for these two reactions are very important. But also the branching ratio is going to be very important here. This one gives reactive radicals. This one is a termination, okay? So one that gives you radicals is going to enhance reactivity. One that gives you termination is going to decrease it. So here are plots then of the rate constants for those reactions. And again, we scrutinize them. Here's a measurement that was performed here at Princeton University. Here's a measurements from Stanford University. And here's a calculation by Aaron Jasper working with Stephen Klippenstein, published in 2009. And that's the rate constant we use in our mechanism. And then again, here are measurements by Stanford. So these black squares and these black squares are from the same study. And then there's other measurements here too. The dashed line is an adjusted rate constant. We're constantly moving this slightly up and down, but you can see it's within the error or the uncertainty of the rate constant. But here's the calculated rate constant from Zhu and Lin, the calculated rate constant from Jasper from 2009, okay? But certainly they're within the uncertainty of the rate constant here. But I can assure you, in our mechanism, you adjust, even within this uncertainty, this rate constant and this one, you get widely different predictions of ignition delay times at this condition of 1250 Kelvin and 30 atmospheres, just because of the huge sensitivity to enhancing reactivity and inhibiting reactivity of those two reactions. So you have to be ultra, ultra careful. And the kinetics are ultra, ultra sensitive to the rate constants that you use for those two reactions. Okay, so you better have good rate constants for those in the mechanism. Okay, I'm becoming tired, and I'm sure you are too. So this is just showing the branching ratio then for the two channels. So this is the methoxy plus OH channel here that dominates at lower temperature, but they actually get closer together. They're converging to maybe 50-50 at 1800 Kelvin or so. But you can see here's the Hong et al. Branching ratio that they have in their mechanism. In our mechanism, the branching ratio is a little bit closer together. It's not as extreme as in the Hong, I think. They're very similar, but they're not as extreme. Okay. Okay, another one is, of course, methyl plus M giving ethane plus M. So methyl recombining to give ethane is going to going to compete with methyl reacting with O2 and HO2 and other species, giving branching. Okay, so this is termination, and it's killing you, right? So you better have an accurate rate constant for that too. If you don't, you're not going to have the decrease in reactivity, particularly in the 800 to 11, 12, 1300 Kelvin range, where the kinetics of HO2 and to a lesser extent O2 are important in competing. So again, as I said earlier, this is oxidation and this is pyrolysis, right? And it's going to go, you have those competing mechanisms, okay? And so we take the rate constants again from the high pressure limit, we take from this study, and actually we take all the rate constants from that study. So, and here are some measurements in the literature, and then this is the rate constant from Blitz, published in 2015. This is the high pressure limit. This is the rate constant at 11.8 atmospheres, 2.8 atmospheres, 0.79 atmospheres. And you can see these are other pressures too, okay? And so we're careful about that, okay? I don't want, another one that's important at low pressure, in low pressure flames, is this one, methyl plus methyl gives H plus ethyl. That's not so important at high pressures, but it is important in low pressure flames. And you have to be careful about including an accurate rate constant for that too. Okay. I'm not going to, there's other reactions here. We have ethylene plus H giving ethyl radical, and vinyl plus H giving, acetylene plus H giving vinyl radicals. Okay, so these are also important to ethane flame speed and other flame speeds as well, right? Increasing reactivity. So where do we take them from? Here again, here's ethane ignition delay, and this reaction, ethylene plus H giving ethyl radical, that's very important, okay? And the ignition delay time predictions are very sensitive to its rate constant. So where are we getting its rate constant? We take it from the calculations by Jim Miller, and he and Stephen Klippenstein have looked at this reaction a number of times in the literature. And anytime a new study of that comes out, we add that immediately to the mechanism, okay? Because again, you can see the sensitivity of the ignition delay times, and hence we want to have an accurate rate constant in there. And he does studies where he's plotting, so he has a high pressure limit, and then there's some measurements in the literature, and then comparing his calculated rate constant against those in the literature. And you can see here his calculations matching the literature data. Okay, and again, this is at the other direction, ethyl decomposition giving ethylene plus H. Again, it's a little bit lower than this 1 point, but that was measured in, is it 1964 or 84? I can't read it properly. But his calculation's probably right. Here's some more measurements by, I think these were measurements by Irene Slagle and David Gutman for ethyl decomposition. Okay, but you can see, well, it says Feng et al. Actually, sorry. So here, there's different pressures. We're at very low pressure and going higher and higher pressure measurements. But this is Jim Miller's and Stephen's calculation as a function of pressure. You see, it's pretty impressive, right? And so, but we include those rate constants in our mechanism. So this is what I was thinking of, the Slagle. Okay, so here's H plus acetylene giving vinyl radical. And you can see again here, there's one data point by Gordon from 1978, and the model is capturing that data point. Okay, here's some more Knazev and Slagle measurements at different pressures for that reaction. And again, it's very impressive that the rate constants are fitting the data. Okay, I'm not going to go into any more details. It's the same. It's the same story throughout. Okay, we look to see what are the important reactions. then we see, well, who's measured the rate constant where, and we scrutinize the rate constant. We plot it as a function of temperature, and we try and make the best fit we can to that rate constant and put it into the mechanism, particularly for these small species mechanisms where the rate constants have largely been measured and there's quite a bit of data available to do this analysis. Okay, I'm going to finish with this and I'll wrap it up. Okay, and this is a nice story where we were looking at acetylene ignition delay times. Let me just show here. Okay. No, I'm not going to go there. Yeah. So here's acetylene ignition delay times that we measured in a study. Okay. So we published this in 2019. It's just one interesting thing to show you. And it's a kind of a strategy that we sometimes use, okay, in mechanism development. Okay, so here are the data. And then here's GRIMEC prediction of the data. Okay, it's an old mechanism, so it doesn't do well, right? But here's our own modern mechanism, our AMCOMEC 2.0. Okay, it can match the data at the very highest temperatures, but certainly, you know, it's not coming nearly within an order of magnitude at lower temperatures. Very poor. And the same with San Diego MEC. But if we take this mechanism for Peter Glarborg, which he published in 2016, really good, right? So there's something in his mechanism that captures these data that we don't, right? And that's sometimes a very nice thing to find, because then you can explore his mechanism and see, well, what's in his that's missing in ours that we can find out, okay? And what was missing is this sequence. So we didn't have a reaction of acetylene plus HO2 producing this radical in OH. And then that radical in his mechanism goes on to react with O2 to give these two products, right? And if we put in these three reactions into the mechanism, our mechanism prediction moves from the dashed line to something that is then acceptable, okay? I'm not going to go. Okay. I think I'm nearly done. Okay. Okay. Okay, one thing I want to leave on. I leave you on this. Okay. And this is an important trend, right? So, and this is a quote from Charlie. He says, "It is very likely that all of the small molecule kinetic mechanisms will steadily converge to a common family of reactions, reaction rates, and reaction pathways." Okay? And I think that's true. As we get more and more, that we will accept that the rate constants for these important reactions are what they are. And this is a conversation I had with Charlie 30 years ago or more. The rate constants are God-given, but we just don't know what they are yet. And we're trying to figure out what they are. But the rate constants are something. They're definable.
Yeah, you're needed.
And we need to get the accurate ones. Okay? So on that, I'll finish for today. Thank you very much for listening. Cheers.